Let's now look at this review problem. Let f be a polynomial with real coefficients that has odd degree. Let's prove that f must have at least one real root. I'm going to show you two different proofs of this. The first proof relies on a fairly simple graphical idea that if a polynomial has odd degree, then it can blow up either upper right and lower left, or it could blow up upper left and lower right. Those are the two ways that the function can blow up as x goes to infinity or x goes to negative infinity. Well, it's a polynomial and therefore it's continuous, and therefore if it's a continuous function and it's up here to the right and up down here to the left, it has to cross the x-axis somewhere in between. Or case B, if it's positive when x is negative and negative when x is positive, then somewhere in between it must cross the x-axis. So that is the idea of the proof, and let's now formally write up this proof, and that will be the first of two different methods for proving this theorem. So let's begin by assuming that our polynomial has the form a sub n x to the n plus da 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 plus a sub 0. Our first case is that the leading coefficient a sub n is positive. If the leading coefficient a sub n is positive, then as x goes to infinity, the limit as x goes to infinity of f of x is equal to plus infinity. Now what does that limit mean? Well, that means that if I want to force f of x to be greater than 1, then I can find some value m, so that if x is greater than m, I'm guaranteed that f of x is greater than 1 if x is to the right of m. So that's what it means to blow up to infinity. That's nothing particularly special about the number 1. I can choose any positive number here, whether it's 1 or 1,000 or 1,000,000. And for any number that I choose over here, I can find a number m, so that x greater than m implies that f of x is greater than that number that I have chosen. Now the number 1 is immaterial. What's important is that there is going to be some number d, so that f of d is indeed a positive number. Now the same thing happens to the left as well. Using the exact same logic, the limit as x goes to negative infinity is negative infinity. Now the reason it's negative infinity as opposed to positive infinity is because a sub n is positive. If x is negative, negative to an odd power is negative, and so I have a negative infinity here. And I believe that's discussed in a previous review problem. So there's got to be some other number, capital L, such that if x is less than L, then f of x can be less than negative 1. And the number negative 1 is nothing special about that. The important thing is that if x is less than some value L, then I can make f of x to be less than negative 1. And so there's got to be some other number c, so that f of c is less than 0. At this point, we now apply the intermediate value theorem. F is a polynomial, and therefore it is a continuous function. And so the intermediate value theorem applies. So if f of d is greater than 0 and f of c is less than 0, then there has to be some point in between so that f of t is equal to 0. And that would be the one real root that is required by the theorem. So that's case 1 if a sub n is greater than 0. Case 2 is similar. And because it's similar, I won't write out all the details. The idea is that if a sub n is less than 0, then the limit as x goes to infinity f of x is negative infinity. And the limit of f of x as x goes to negative infinity is equal to plus infinity. So by similar reasoning, there must be a real root. The difference, of course, would be that the first statement you'd find a number that's negative, and that has a negative value, and the second statement you find a number that is a positive value, and there must be a value that's equal to 0 in between. I don't write out the details in this video. I encourage you to write out the details very much like what's on the screen right now. So that is one idea for proving this theorem using the intermediate value theorem. Let's now proceed with a second way of proving this theorem. And this second way is based on the unique factorization theorem for polynomials over the real line. The statement of the unique factorization theorem is that f must be written as, actually uniquely written, as the product of a non-zero constant, monic linear polynomials, and or monic irreducible quadratics. So that is true for every polynomial that has real coefficients. However, the function f has an odd degree. So the polynomial terms in the factorization cannot just simply be irreducible quadratics. By that I mean if we have a quadratic polynomial times another quadratic polynomial times another quadratic polynomial times another quadratic polynomial and so on, then the leading term would have a term that has x to some even number, where the even number is 2 times the number of polynomials. Well, that can't happen because f is odd. And because that cannot happen, that means at least one factor of f must be a linear polynomial. That basically ends the proof, because by the factor theorem, that because it has a linear factor, that means that f must have at least one real root that corresponds to the x-intercept of that linear factor. And so that's the second proof based on the unique factorization theorem for polynomials over the real line, also using the factor theorem.